Okay, so remember last time, let me maximize this, right? We learned about this thing called diode. What is a diode made of? I'm sorry? Yeah, p-type semiconductor and a n-type semiconductor stuck to each other, right? So that's what this is, right? And then when they get stuck together, what happens is that the n-type, it doesn't have extra electron, it's not charged, right? But there's a tendency for the electrons from the n-type, right, semiconductor to migrate to the p-type semiconductor, right? This is called the donor, and this is called the acceptor also, okay? And this creates an electric field between them, right? Because now, right, after you sandwich them together, this side becomes slightly negatively charged, this side becomes slightly positively charged, right? Okay? So when you sandwich them together into a, um, between n-type and p-type, that's when you get them to be slightly charged in this region called the depletion region, right? And therefore you have this potential across it because this is slightly positive, slightly negative. When you have positive charge here and negative charge here, it basically creates potential between them, just like on the capacitor, right? So now that we sandwich two semiconductors together, okay, the next device, okay, what would you think the next iteration of this type of device is going to be? How many semiconductors we're going to sandwich together? Three, okay? Okay, and this is the invention of the transistor. And if you did this in 1956, you would win the Nobel Prize just by saying that. Okay, that's the idea. You sandwich three different semiconductors together. Okay, and this is the physical picture from Shockley Bardeen and Brenton, who won their Nobel Prize in 1956 for inventing the transistor. Okay, this is the actual physical transistor that's in like a, I think it's probably in like the museum in DC, where he placed basically this is one type of, this is like an N-type semiconductor. The thing in between is the P-type, and then the bottom one is the N-type. It's literally like you just got a bunch of semiconductor stuff and then you just stuck them together and see what happens. Okay? And here's all the little wirings, okay? So don't do wirings like this. Now we have breadboards also, right? Okay? And you can see this in a museum. And this one transistor, right, basically gave birth of all of modern electronics, okay? Because, right, for example, inside all of our devices with all these processors and stuff like that, all of those are made of billions and billions of these transistors. Of course, this one is about this big, right? Right, you're not going to fit billions and billions of those into your phone. So they make them smaller and smaller and smaller until, you can fit on the tip of a pen millions of transistors by creating basically lithography on the size of maybe on the, I think now we're doing like 35 nanometer lithography. You can like make things that are size of like 35 nanometers, which is like, which is crazy. It's like 100 atoms, right? That's the structure that we're making. Okay. So with that, I'm going to go back to this LISIC video that I start showing you last time, right? So do you guys want to just watch the whole thing where it describes the diode, the transistor, and that way we have a little review also, okay? So let me get this to play again. Turn this thing on. Power. Okay. You can skip a little bit of the intro. Oh, and also want to make sure that I'm using the mic, the output of the speaker instead of my headphone, because that would just make me deaf. And yeah, it's on headphones right now.
Electron flow. If you can increase the base current, the collector current will increase proportionally. This is a clear case of current amplification. The kind of transistor we have discussed is called a bipolar junction transistor. Let's replace this representative transistor with a realistic one.
Pause. Stop. Stop. it's saying to stop.
You can further improve the amplification by introducing one more
Yeah, I
transistor.
pushed it too many times. Okay, there it goes. Okay, I wish I had stopped it at that picture just like 5 seconds ago. Let me see. I'm gonna scroll back. Let's not try that. Okay, so hopefully, I'm just gonna draw on the side. It's pretty easy to draw, right? So you have some either N-doped or P-doped stuff, and for this case, let's just make this N-doped, and a thin layer of P-doped, and then another layer of N-doped, okay? And the idea is that, right, if you connect a power supply between the two sides, right, so for this case, maybe this is the direction of the battery we connect it to, okay, right? The transistor does not conduct anything, right? And so that's because you basically have, in this case, right, this will be the reverse bias diode. This is the forward bias diode, right? But then the reverse one is going to be blocking the current, okay? So that's no good. And the idea is then, well, what we're going to do is we're going to connect to the middle here with a different power supply, right, to this other side. And basically, this part of the circuit acts as a switch. Another way to think about this is like a valve even, okay, right? And if you turn this valve on, it allows the current to flow straight through. And then the amount of current flowing through this valve is proportional to the amount of current that is flowing through the entire transistor with a proportionality factor of beta. And this beta is actually basically determined by the thickness of the p-dope part versus the thickness of the n-dope part, okay? Okay. And so you can think about a transistor is kind of like the little valve in your garden faucet or your closet, right? You can turn that and then have the current flow as fast as you need it to be, okay? It's sort of a nice little thing, okay? Right? And on a circuit diagram, what they would look like is basically the way you would draw it, and this is draw one, okay? Let's do that in black, right? You draw it like this. And then depending if it's p-dope, so NPN versus PNP transistor, you would draw one of the arrows going out, okay? You draw a T, and then you draw the two little bar, and then you draw either the arrow going into the transistor or going out of the transistor, okay? We're gonna focus mostly on this type, which is gonna be the NPN transistor. Um, if you see a diagram where you have the current flowing into the transistor, those are called PNP type transistor. They're very good for current amplification, but they are slower switching. And you know the details of this is just based on their kind of structure, but we don't really need to go too far into it. If you're really interested in reading all the technical details about the difference between the two types of transistor, there's a little link from Electrical for You. .com that you can read about, and in this class we'll be mostly using well, actually always using uh, NPN type of transistor. That means, right, the picture here, right, you start off with the N-dope region, and then you have a little thin layer of P-doped, and then you end up with the N-dope region, okay? That's the type of transistor we're going to be working with, okay? Okay. In order to figure out how these transistors will behave uh, in your circuit, um, I think some textbook uses. I'm not sure if this book uses this. I call them, or other. I actually stole this from other textbook. They call it the golden rules of transistors. Okay. If you just follow these rules about their behavior, you can exactly predict how a transistor will behave in your circuit. Okay. Right. Interesting. Okay. So rule number one, right? A transistor is a diode, right? To begin with, well, it's two diodes sandwiched together, right? So that means, right, there's going to be a voltage drop whenever you go across a transistor. So I'm going to draw the little transistor. Let's have this picture down here, okay? Okay. Rule number one is that well, let's just get some nomenclatures in place, okay? The part, basically the part where you connect the P to the P dope region is called the base, okay? Okay. the part where you connect the positively biased, meaning the positive end of your battery, so let's say over here, okay, that's called the collector, okay? C stands for collector, B stands for base, okay? C stands for collector, is where you're collecting the charges, okay? And E stands for emitter, okay? That's where the charges come out and emits, okay? Hopefully those words make sense, okay? Okay. All right, so rule number one is that the voltage from the base to the emitter has to drop, okay? And this voltage drop depends on basically the model of transistor you have, the ones we're going to use in this class. It's going to have a drop of 0.65 volts, okay? One diode drop worth of voltage, okay? So whatever the voltage at the base is, right, and you compare it to the voltage at the emitter, right, the base is always going to be higher by 0.65 volts. Okay, not too bad. Okay. So rule number two is that whatever current comes out of the emitter, okay, is going to be bigger than the base current by a factor of beta, right? This is this is basically, think of it as like the amplification of current, okay, out of this transistor. Remember when that little video, a lot more little white dots came out of between, travel between the emitter and collector compared to the amount of white dot that travel between the base and the emitter, right? Right. More current went out, okay? Right. Let's go back to this picture here, the more physical picture, right? Right. Remember when they were drawing the little white dot? There was a bunch of, well, now they're purple dots, sorry. There was a lot of purple dots going this way, but then a few going this way, right? Okay? By controlling how much current is going between your P and your N region, you can actually control how much current is flowing through your N and N region, okay? The two N regions, okay? So that's rule number two, okay? And the factor between them is beta. And for our transistors that we have, beta is going to be approximately 100. Okay, so in a lot of your calculations, just say beta is 100, unless it tells you beta has to be 200. So there are transistors that are like has a bigger current gain than application than the ones we have. Okay. Okay. So that means the current that's coming out of the collector, right? So now we're just applying Kirchhoff's law, right? Junction law, right? The current that's coming out of the emitter is the combination of the current that's going into the base and the current coming out of the collector, right? Right? They combine together and come out on the emitter, right? So that means the current that's coming out of the that's coming from the collector is going to be also proportional to the amount that's coming out of the emitter by this number called alpha. Okay, we don't know what that is yet. Okay, and in fact, alpha will just turn out to be approximately 1 anyway all the time. Okay, then what you can do is then by using Kirchhoff's law, you can relate it. Well, beta has to be this alpha over 1 minus alpha. Okay, and then alpha is beta over 1 plus beta. Okay, and in most of our calculations, unless the problem asks you in detail what alpha and what beta has to be, right? Just think about alpha is approximately being 1 and beta being 100, okay? Because you can see that, well, if I plug in 100 here, right? 100 over 101 is basically 1, right? Okay? Okay? Right? The last rule is that, well, the collector must be at a higher potential than the emitter, right? Because if it's not, then current's not going to flow that way, right? It's going to try to flow backward, okay? Okay, those are the 3 rules, okay? Okay? All right. Let's try to apply these 3 rules to this simple circuit where I have some constant voltage supply, you know, a battery or something like that, okay? And then that I can, you know, turn up and down. I put a resistor at the source, meaning the input, right? I just connect that resistor right into the base, right? And then the output, into the output of the and see what happens to the output of the transistor. And this is assuming that we already supply um, basically, a bigger voltage source to this, okay? And that way you can actually make sure that that's obeying rule number 3, basically, okay? Okay. And let's see what happens, okay? Okay. So we're going to apply the 2 rules that, okay, that, whoops, you can't see it over here. Here, come on. Okay, there's 1, 2, 3 here, right? That the voltage across the base to the emitter is approximately 0.65 volts, okay? And the currents gets amplified, right, by a factor of beta. In this case, just use beta at 100, which is basically what our transistor that we're using in this lab going to be, okay? The collector must be a higher potential than emitter, which I already kind of fixed by putting a power supply to the collector and the emitter, and making sure the emitter is at the high potential and the collector is at a high potential, the emitter is at a low potential, right? Okay. Right. So let's say, right, the voltage at this point is at 0. Okay. Okay. Right. So in order to figure out what's going to happen is that, well, we know that this point of the circuit is tied to the ground, right? This is ground, right? Right? This is at 0 volt all the time, no matter what you do, right? So if this point is at 0 volt and this point is at 0 volt, right? What will be the voltage difference between the base and the emitter? Put E here. You're going to put a little B here, put a little C here. If the voltage difference between the base and emitter will be what in that case? If they're both at 0. What's the difference between 0 and 0? 0. Okay. Okay, so in this case, right, the base and emitter does not have this voltage difference of 0.65 volts. Okay, in this case, the transistor is actually completely off. Okay, okay. When the transistor is off, that means nothing goes through the transistor. It's just a diode that you didn't overcome the potential for. Okay, so in this case, you can write 0 as the base current, right? Right? And then the collector and emitter current is basically going to be beta times 0. So beta times 0 is still 0. Okay, not that great. Okay, so since no current flow through this resistor, right, if no current flow through your resistor, the voltage difference between across that resistor is also 0, right? So if the voltage difference between across this resistor is 0, you go from 0, difference of 0, you get to 0, right? So a lot of zeros around, okay? Okay? All of this just becomes 0, okay? All right? All right, what if I turn my little power supply up until Vs becomes 0.5? Okay, let's see what happens then. Okay, becomes 0.5. 0.5 is still not enough to overcome the diode inside the transistor, right? So the transistor still stays off. Okay, that means the current at the base is off. That means the current at the emitter is still off. Okay, the voltage at the emitter is always going to be 0, actually, because we tie that to 0. Oops, I wrote that in the wrong place. Okay, in this case, right, no current is flowing through the resistor. The voltage drop across that resistor is still 0. What is the voltage at the base? 0.5. You didn't change it, right? If no current flow, it doesn't change the voltage, right? Right. So that's the first non-zero number. All right. Now let's do something more interesting. We're going to crank the voltage up to 0.7. Wow. Okay. Now, right? Now, initially, you're going to have 0.7 volts of voltage here, right? And then that's bigger than that 0.65 volts that we need in order to overcome the current. Okay. So in this case, right, we're going to enforce the fact that the voltage difference between the emitter and the base has to be 0.65. That means, right, from here up to here, there has to be 0.65 difference, okay? That means the voltage at the base has to be 0.65, right? Okay, does that make sense? Okay. Now, there's a voltage difference between the source and the base now, right? Right? V from the source minus V to the base has to be how much? 0.05 volts, right? Okay. And let's using a resistor value of 100 ohm, right? That means how much current flow through that source, that resistor. What's the formula for it? Right? That's just Ohm's law, right? You move 2 zeros over 0.0005 amp. In other words, about half a milliamp. Okay. What does that equal to on my table here? It has to be a current, so it's one of these two. Which one should it be? It's the base current, right? Because right now you have a single stream, right? The current through the resistor is half a milliamp. Whatever is going through the base is also half a milliamp, right? Okay. So we can just write this down. Okay. Right. Once we have that number, we instantly know what the current through the emitter is because it's just going to be 100 times bigger, right? So this is going to be 50 milliamp out of the emitter, okay? And the emitter voltage is always going to be 0, by the way. Doesn't matter, right? It's just placed there to trick you guys, okay? All right, let's see what happens when we crank the voltage up to 1 volt, okay? Okay, what will be the voltage at the base in this case? No calculation needed. 0.65, right? Because emitter is always tied to 0. The difference between the emitter and the base always has to be 0.65. Okay? In fact, I can write this for the next one, right? The negative is going to get a little funky, okay? Okay? Okay. If the voltage difference between the source and the base is 0.35 volts, right? How much current would there be? Let's see how I got that number. Basically, I just replaced this with 3, right? This is with 3, and replace this with 3. Okay, so 3.5 milliamp, right? Right, right. Because the difference between 1 and 0.65 is 0.35 volts instead, right? Okay, okay. Once we have that number, right, we can multiply this number by 100. So 350 milliamp will come out of the emitter. Okay. Okay. And then when we crank it up to 1.6 volts, right, we're going to get 10 milliamp out of here, or basically 1,000 milliamp out of the emitter. Okay. What do you think will happen when the voltage source is negative? Will the transistor turn on or not? It will always be off, right? So if it's always off, then you just zero all these numbers. Okay? Okay? Does that make sense? How to use these kind of like table of cases of voltages to figure out what's going to happen on your circuit? Okay, this is very useful, right? Especially when you start dealing with more and more complicated transistor circuits, okay? All right. Okay. Any questions about this? Okay, how to use these? You're basically kind of just using these two rules, right? The voltage drop and the current amplification. Okay. All right. Any questions? Sorry, I didn't wait to answer. One okay? Funky things. In fact, if you want to go into your kit and take out one of the transistors, you can look at it. So it'll be one of these little black things with 3 legs. Okay. Okay. And in the 4th lab, it'll tell you which one is the base, which one is the emitter, which one is the collector. Okay. Right. 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 Basically, I think usually the middle pin is the base, and then one of the pin is the collector, one is the emitter. Basically, you have a little circuit that you can plug in like this. Okay. Okay. Now, let's do a little bit of mathematics to simplify some things that may be a little bit confusing. Okay? Okay? So, when, in fact, I can, if I have my mouse, I can actually show you, right? Along with devices, right, it takes like two AA batteries, and then the way they arrange these AA batteries like this, right, where you connect this to this end, right, you connect this to this end. So if this is each of the batteries 1.5 volts, right, if you look at these 2 points, what do you get? How many volts do you get out? 3 volts, right, because you just stack them together, and then you get a higher potential, right? So potential, just like potential energy or other type of energy, right? They add, right? You can just add them, right? It's just a scalar. Okay. So the same idea happens when you're mixing AC and DC voltages. And some of you guys experienced this already when you connected your AC supply into your DC supply in lab 2. And so unless you want to do that on purpose, don't do it, okay? Unless you know that's what you want, okay? So that means if you have some constant voltage, V sub B, right? The voltage at the base, right? And then on top of that, you have some time-dependent thing, which is the lower case, right? The total voltage is just some dependence with the sum of those two voltages together, right? Right? I'm just doing a little bit of math just to make sure that we're not doing anything funky, right? Same thing can be said about the collector voltage and the emitter voltage, right? Nothing too crazy there yet. And the nice thing is that, right, current does the same thing, right? When you add two currents together, right, they just add, right? If you had 1 milliamp plus some time-dependent milliamp, right, it'll be 1 milliamp plus that time-dependent milliamp, right? That's going to be changing over time, okay? Okay. So same thing for the collector and emitter, okay? All of these equations, we're going to get a result that's going to turn out to be, oh yeah, that's obvious, but, okay? All right, so what's happening is that in order for you to turn on your transistor, okay, right, you need to have a voltage source that's a constant 0.65 volts above the emitter, right? That's rule number 1, right? So that means whatever the voltage at the base is, it has to be whatever the emitter voltage is plus 0.65 volts, right? It's just a fact in order for you to turn on that transistor. Otherwise, it'll just shut off and nothing will happen. Okay? Right? What we can do now, right, is go back up to here and note that, well, the voltage at the base is the sum of these two guys. The voltage at the emitter is the sum of these two guys, right? If we substitute that stuff in here and then rearrange so that the constant part is in the front and the time-dependent part is in the back, right? I just kind of shovel the terms around, okay? Right? So the criteria for you to have a transistor that is on the on mode, right, is only that the constant part of the base voltage and the constant part of the emitter voltage has to be bigger than 0.65. Well, it has to be exactly 0.65 actually. Okay? The time dependent part, it can be whatever it wants to be. Okay? Up to a point where the transistor stays on. Okay? And we're going to see this effect in a little bit when we're with an analysis of how the voltages could change when we want to measure the voltage at the base compared to the voltage at the emitter. Okay, so with this criteria, the statement is that, well, whatever the time-dependent part of the voltage at the base is going to be exactly the same as the time-dependent part of the voltage at the emitter. Okay, that's just solving this equation by plugging this in here, right? 0.65, right? This whole thing, 0.65 equal to minus V sub B. I'm going to do a lowercase also. Minus V sub E. That's equal to 0.65. And technically, to put a little delta, this goes away, right? So that means this has to be equal to 0. That means these two things has to equal to each other, right? Right. This little algebra stuff. All right. So that's the result we're trying to get out of this. This was the last 10 minutes of my life, right? Of our life. All right? And let's see what happens when we have a time-dependent voltage applied into a transistor circuit. Okay? This is known as the emitter follower circuit. Okay? And you're gonna see at the end, it's like, this is kind of a pointless circuit, but then I'm gonna dispute that. Okay? So you have a transistor, right? And you have some voltage source, right? That's a combination of some constant one and some time dependent part. Okay? So the total voltage here is the sum of these two things. Okay? Right? The voltage at the emitter is also a combination, right? A sum of the constant part and the emitter part. Okay? Up here, VCC, okay? This is the voltage at the collector. Okay, so when people write VCC, what you're assuming is that you basically connected your collector to some high voltage supply that allows you to fulfill criterion number 3. Okay, this is basically say, okay, I connected this to a 15 volt constant supply so that whatever is going on in between is going to be able to supply at least 15 volts to the output. Okay. Okay. All right. The only difference is now we're going to move the resistor from there to the emitter. Okay. We're going to connect it to the emitter between that and the ground. Okay. And this is going to be our V in, and this is going to be our V out. Okay. The emitter voltage is going to be our V out, and the base voltage is going to be our V in, which is basically the sum of these two things, right? Okay. So once again, we're going to apply the golden rules. So we're just going to apply that. Well, the voltage at the base and the emitter has to be 0.65 volt, just like a diode. Okay. And the current gets amplified by a factor of beta, which is for our resistor is going to be 100. Okay. So I'm just going to go through this kind of mathematically. Okay. Okay. Let's take the resistor at the emitter to be 100 ohm and our voltage supply, right, up here to be 12 volts, okay? So what happened is that if the emitter goes over 12 volts, the transistor actually turns off, okay? You cannot go over 12 volts, okay? Okay. So with what we just previously derived, right, the voltage, the time-dependent part of the voltage at the emitter has to be the same as the time-dependent part of the base, okay? And the offset part, right, the voltage, the constant part of the base is going to equal to the constant part of the emitter plus 0.65 volts, okay? Right? The amount of current flowing through the emitter, right, if we just apply Ohm's law here, right, it's just whatever the voltage there is divided by that resistor, right? Hopefully that's not too bad, right? It's just putting the R underneath. Okay. All right. So let's see what this will look like. Okay. Okay. So the base, right? Basically your input V in, right? Is this dashed line here, and it oscillates up and down, up and down. Okay. Okay. And in fact, the dashed line goes below 0. Okay. And then the output is the solid line, V out. Okay. All right. You can see that the solid line and the dashed line follow each other with a space between them. How big is that space between them? 0.65 volts, right? Because, right, the constant part is going to be offset, right, between the base and the emitter by 0.65 volts. Okay. Okay. They're going to follow each other until it gets to, right? Basically, what happens at V in equal to 0? Why is it actually? It gets to that part where V in. I have to zoom in a little bit to show you guys this. Okay. From here to here, right? How big is that voltage difference? 0.65 volts, right? So until the input gets to 0.65 volts, right, they will follow each other. When the voltage at the input reaches 0.65 volts, what happens? Or 0.64 volt, just slightly below 0.65. Right, it turns off the transistor. When the transistor turns off, right, going back up here, right, when the transistor turns off, how much current flows through here? Zero, right? Zero voltage goes through here. That means the voltage between VE and ground is zero, right? So right away, when your input gets below 0.65, your voltage basically just drops to zero. Okay? Until it reaches 0.65 once again, then you turn the transistor back on in order for you to drive current through it. Okay? This is the part where the transistor is off, right? This is the part where you get on. Okay? This is the on part. Okay? So these transitions are very important to note, okay, when you're designing circuit, okay? Because if you actually wanted to, have the output to be exactly the same wave, you design the circuit wrong, right? Because it's going to get chopped off on the bottom here. Okay? Okay. The opposite effect can happen, okay, if your voltage supply is not big enough in order to supply enough voltage to get 12, well, whatever the biggest output that you're going to want, okay? In this case, right, they also fall in the same line. You have this 0.6 volt difference between the input and output, right? But notice that the output can never be below, above, what do you guys think this number is at? 12 minus what? 0.65, yeah. So, or 11.35 volts, okay? So when you have a voltage power supply, right, this VCC number, if it's at 12, your output can never exceed 11.35, okay? Basically, the top of your wave just gets chopped off, okay? Okay, okay. Another name for this is also known as saturation, okay? Okay, you basically saturated your circuit. You cannot go above that, okay? Okay. Okay, so what we can do is also calculate the current that's coming out of the emitter, right? Because a lot of times we actually are concerned about the current, not about the voltage, okay? Okay. This requires me to go back up here, right? The current at the emitter is VE over RE, right? Okay, what I'm going to do is that, well, obeying rule number 2, right, the current at the base is going to be the current at the emitter times beta, right? Okay. In fact, it's technically actually 1 plus beta, okay? Because this is the current from the collector. That's actually, oops. This is the current from the base, and this is the beta times that is actually the amount of current from the collector. But since beta is like 100 plus 1 is basically 100. So a lot of times you can just, say that that's basically just beta. Okay? 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 And remember, one of the things we figured out was that the voltage at the base is basically going to be approximately the voltage at the emitter, while the time-dependent part is going to be the same as each other, right? They're going to be offset by this constant 0.65 volts, but they're going to be the same as each other, right? Right. So let me copy the previous one over. The current at the emitter is equal to the voltage at the emitter divided by RE, right? Right? Okay. So I'm replacing the voltage, the time-dependent part of the emitter voltage with the base voltage, right? That's all I'm doing, the right-hand side. IE, I'm replacing, right, with beta times IB, not I beta. Okay. And there's going to be a point to this, okay? Unfortunately, the book always keeps this 1 plus beta thing. I'm just going to replace that 1 plus beta with beta. Okay. So what's going to happen is that basically your input and your output, the time dependent part, is just going to be the same as each other. Okay. Right. So in order to get input equals the output, you put a transistor and a resistor in there, right? In fact, you have to put a voltage supply in there too, right? So this seems like a pretty useless circuit, right? Because you could have just look at the input and not bother with all this transistor stuff, right? Right? There is a use for this circuit. Now we're going back all the way to chapter 1, okay? Remember when you're designing circuits, right? You want your output impedance to be low and your input impedance to be high, right? That way when you connect a output to an input, the input is not affecting the output. Remember that? When you did your voltage divider, right? When you put 1 meg ohm here, 1 meg ohm here, this makes a very large output impedance, right? That affected, whatever the R load is doing, right? You guys remember that from lab 1, right? Right? So what you're supposed to do is put like a tiny resistor here, maybe 100 ohm here, 100 ohm here, then it won't affect the output, right? Okay? Right? So now let's think about what is the input impedance of the emitter follower. Okay? I think I'm going to redraw this circuit. Well, the answer is down there, but I'm going to redraw this circuit anyway, just so we can figure out what that is. Right? That's basically the circuit, right? Forgot the resistor. RE. Okay? 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 So how do we determine the input impedance of something, right? You think about what's the input here and how much impedance is going to be needed in order for that current to reach ground, right? How hard is it to get to ground, okay? Okay. So let's see. So whatever the current through the base is, right, is going to be amplified by a factor 100 or beta at the emitter, okay? Okay. So, so that means this basically is amplifying this current by a factor of beta also, okay? So whatever the input is, you can just kind of assume that once the transistor is on, you basically don't have any impedance through the transistor, okay? Once it's turned on, okay? Basically whatever the input impedance is, it gets multiplied by a factor of 100, okay? In this case, right, the only impedance from the current to go to ground is RE, right? Okay? Right? It gets amplified by a factor of this beta. The book does 1 plus beta, just to be technically correct, right? But beta is 100, so 101 is basically 100 to me, okay? Right? You can say that's approximately beta. So what this does is basically it increases your input impedance by a factor of 100 just by putting a transistor in the circuit, okay? Right? So we want high input impedance, so that makes it good, okay? Right? Output impedance, okay? Right? Do you guys remember how to deal with output impedance? Was that magic name that you guys hate to deal with? Which equivalent? The Thevenin equivalent, right? Yeah. So the output impedance is basically going to be whatever the Thevenin's equivalent resistance slash impedance is. Okay? Okay. In this case, we actually have to like add a little bit of something into the circuit in order to do that, because you can't really do a Thevenin equivalent of a transistor and a resistor, because once the transistor turns on, right, the impedance of the transistor goes to 0, right? So what the book did is basically it added a resistor at the source in order for you to calculate what that Thevenin equivalent is. Okay? Okay? And basically what happens to the output impedance is that the output impedance becomes, right, RS divided by beta. Okay? It reduces the output impedance by a factor of 100 by adding a transistor in the circuit. Okay? which is the other point we want, right? So, right, by putting this little transistor in there, the input impedance increased by a factor of 100, the output impedance decreased by a factor of 100. So whenever you connect something to the input and output of that circuit, right, it's less affecting. They're not going to, lower the output just by connecting a load to your circuit. Okay. Okay. It makes your circuit a lot easier to work with. I can just build a circuit, pass it to you. I don't have to worry about, oh, Alwyn, are you going to connect a 50 ohm load onto this my circuit, or you're gonna put it in a 5 meg ohm, right? Because if I have a very high input impedance and a very low output impedance, I don't have to worry about that. I just give it to you and it works, right? And this is how, right, I'm able to, connect, this circuit inside here into the 120 volts there and not worry about, oh, how much load am I drawing? Am I gonna like break my laptop if I draw too much load, or if I'm gonna not have enough power if I don't draw enough load, right? Okay, so designing circuit that has these properties, right, by just adding a transistor to it, makes it a lot easier for it to be useful to other people, at least. Okay. All right. So how much time we got? 57. Okay. So this is going to be the last circuit we're going to talk about, and you're going to build this next week. Next week. Okay. Which is the common emitter amplifier. It's going to be our first amplifier. Okay. So, okay. The only difference between this and the emitter follower is that you also put a resistor at the collector. Okay. Remember the previous one was just this. Now we put a resistor at the collector. Okay. Right. This is still going to be your input. Right. There's going to be some time dependent part. Right. Plus some constant. Plus some time dependent part. Oh, this is actually, yeah. This is going to be confusing. Okay. This part going to have some time dependent part. Okay. Okay. And we're going to call this part V out, which is actually, yeah, it is. It is going to have a time dependence on it. Okay. Right. So instead of taking the output at the emitter, we're going to take the output at the collector. Okay. All right. Add it one resistor and take the output at the collector. Okay. You would think, well, why would this make an amplifier? That doesn't make any sense, right? Okay. So let's just pick some numbers for our resistor. Make our collector resistor 1K. Make our emitter resistor 100. So there's a factor of 10 between them. Okay. And our VCC is at 12 volts, so that, the maximum output of my circuit is going to be 11.35. Okay. Okay. First thing to note is that whatever the voltage at the collector is going to be VCC minus IC times RC. Why is, can anyone tell me why? Which law tells me that? Just Ohm's law, right? Whatever the voltage is up here, right? Well, sorry, whatever the voltage is here, right, has to be a voltage drop from VCC, right? That's just because that's the connection between them. Okay? Just like before, right, the current at the emitter is going to be equal to the voltage at the emitter divided by RE, right? Right. That's the same thing as the previous circuit we just had. Okay. We're going to substitute in the voltage at the base to be the voltage at the emitter. Sorry, voltage at the. We're going to substitute for voltage at the emitter with voltage at the base, right? Not changing this equation too much. Okay. But, okay, the collector and emitter current are basically the same. They're off by like 1%, so but we can do that substitution approximately, right? Okay. That means, right, the current at the collector is also going to be basically the voltage at the base divided by RE. Okay? Okay. The time-dependent voltage at the collector, right, is going to be, well, whatever minus the resistor value at the collector times the current, right? This is Ohm's law once again, right? Okay. Well, look at this. I have this to substitute exactly into here, right? So that means the voltage, the time-dependent part of the voltage at the collector is going to be whatever the voltage at the base is times this ratio of RC over RE. Okay? Right? With a negative sign. It's actually going to flip the signal. Okay? Okay? So, remember up here, the ratio of RC over RE is 10. Right? So, the gain, right, from the output to the input, right, is negative 10. Okay? So you just amplify your input by a factor of 10, but then it's upside down, unfortunately, because this is an inverting amplifier. Okay? Okay? So unfortunately, this looks a little funky because, right, you have very small voltages here, but then the output is going to give you a very large output because you just amplify it by a factor of 10. Okay, so this is the input voltage, so it's going up and down, right? Right. This is actually a lowercase. Okay, don't get a little bit confused by that. Right, up and down, right? Okay, it's a very small voltage, right? It goes from like, 0.5 to maybe 1.5. Okay, right? But this gets amplified into a big giant wave where it could go up to 12 volts to about 2 volts. But notice that, right, this is the peak of the input, but this is the trough of the output, right? So they are inverted relative to each other, okay? In fact, when you do this on your scope, you can just make the channel 1, right, the scale 10 times smaller than your output, and therefore they will actually look the same if you did this exactly at 10, okay? Okay, their size will look the same, but then the scale is different, and you will see that, what you will see is like it'll look like this, where one wave is like this, the other wave is like this. Okay. Okay. So this is going to be your first amplifier that you're going to build next week. So let's see. Anything else? Just a little bit more like side information that's not going to be on your labs or your tests, right? This is something called Moore's law. Probably have you guys heard of it? Where the number of transistor in a processor basically doubles every year, right? Or is it? I think it doubles every 6 years or something like that. Okay. So for example, right, the number of transistor in my computer at home, where the heck is it? It's a AMD Ryzen. Okay. Okay. So my little processor have 5 billion transistors in it. Okay, 5 billion of those, that two little black thing with a triangle in it, but of course miniaturized. Okay, okay. So, and I don't know if you want to look up your CPU and just look up how many transistors are inside your CPU, so you can figure that out. Okay. I think this is up to date to 2020, so if you have a very new CPU, you may not see it. Okay. In fact, you can see this if you just take a little magnifying glass and you're willing to smash your your computer open and then look at it, you're going to see all these computer cores, which each of these has something on the order of 2 to 5 billion transistors in it. Okay. Let's skip the discussion on field effect transistor. The thing to note is that field effect transistor is easier to make using lithography, which is how all of our processors are made these days, and that's why they use this geometry instead of the 3 sandwich geometry that we're using for our transistor in here. Okay, so the operation of it basically works exactly the same way. Okay, you have a collector, an emitter, and then you have a base, okay? But now, right, they call it a gate, a source, and a drain. They're kind of like synonym of each other, right? Okay, if you know the operation of it, okay? So I'll skip this video on lithography because that's going to be like a 10-minute video.